we're going to start getting into the covalent bonding, right? Something that you probably all heard about, but we haven't really discussed a lot yet in lecture. So that we're going to start doing that today. So to get into that, let me remind you a little bit about what we learned last chapter when we look at the periodic table. And you know now that when you're dealing with the main group element, you can predict what the charges would be on the ions that would form, right? This is a skill that you've been using a lot. If it's from group 7 here, you know that like fluorine, chlorine, bromine, iodine, right? Those are the halogens. They're going to gain 1 electron to become most stable in forming an ion. That gives them a 1- net charge. If it's oxygen or sulfur, selenium, tellurium, here in group 6, they would gain 2 electrons. And I've conveniently always described this without going into group 4 at all. And only one student actually asked me, well, what do we do about like carbon and silicon and so forth, right? In that family. Well, these are going to be elements that aren't going to gain or lose electrons. These are going to be the ones that are going to share electrons to become more stable. Now, in doing so, as you'll see, they're still going to have a full valence shell, but they're going to have a full valence shell because they're sharing electrons with their bonding partner. They're not gaining or losing electrons with their bonding partner. Okay? So these are going to share only. And in doing so, we're going to form covalent bonds. And in fact, the term covalent comes from covalence electrons. They're sharing valence electrons. Now, it's not absolute, okay? Well, it is absolute when it's in group 4, right? Carbon, silicon, germanium, tin. If you're looking for a rule of what's going to be covalent and what's going to be ionic, it's pretty standard when you have the lighter elements. So in period 1, period 2, period 3, and so forth. As you get to the heavier elements, these so-called rules for whether it's a covalent bond or an ionic bond, it's going to get a little murkier there. When we're dealing with group 4 for carbon and silicon, those will only share. But when we have nitrogen and oxygen, or phosphorus and sulfur, so some of the group 5 and group 6 elements, and some of the group 3 elements as well, we will find that those will sometimes form covalent bonds and sometimes they'll form ionic bonds as well. So for example, we've been describing in the previous lecture, oxygen might form the oxide 2- ion. Or nitrogen might form the nitride 3- ion. And it will do that when it's forming ionic bonds. But you're also probably familiar with molecules that have covalent bonds, like H2O. Okay, in H2O, and we'll be modeling that in just a moment, in H2O, oxygen's involved in covalent bonds. It's sharing its electrons there. It hasn't gained 2 electrons to become the oxide ion. The same with nitrogen. You may be familiar with something called ammonia, right? NH3. There, nitrogen is involved in covalent bonds. But it can be also involved in an ionic bond if it gains 3 electrons to form the nitride ion. Okay? So I know students always like to look for, black and white rules of how we name these things. And when it comes to bonding, whether it's a covalent bond or an ionic bond, it's not so polarized. There's actually a whole sliding spectrum between being completely covalent and being completely ionic. So if I were to challenge you with, say, here's a compound and is it ionic or is it covalent? That's not always an easy task to do because there's lots of shades of gray in there. However, there are some cases where you can always count on it being ionic or covalent. And so in general, let's just put some general rules up here. So in general, if you have a group 1 or a group 2 metal, and it's forming a compound with a nonmetal, we're going to always consider that to be ionic. Okay? And if we have two nonmetals, so if we have a nonmetal plus a nonmetal, we're going to consider that to be covalent for sure. When I say for sure, I mean for the purposes of what we need to be focused on in this class. So let's highlight that, just so you have those general rules in mind. So group 1 and group 2 metals, those come from on the left-hand side of the periodic table. The nonmetals are on the right-hand side of the periodic table. So another way to phrase that is if you're dealing with a compound and the cation comes from the left-hand side of the periodic table and the anion comes from the right-hand side, it's for sure going to be an ionic compound. And if you've got two nonmetals like carbon and nitrogen, and carbon and oxygen, or nitrogen and oxygen, and all of those, okay? There's all sorts of combinations there, okay? Those are going to be covalent bonds for sure. And there are going to be lots of things that you're going to see that are somewhere in between, and don't worry about identifying those as being ionic or covalent, all right? And as you'll see when we get to the end of this discussion sometime next week, I'll remind you that there really is a sliding scale of being completely covalent versus completely ionic. Okay, so just to add to this a little bit, so these here and here, these can go both ways. So these can share, or these can form ions, meaning that they can be involved in both covalent bonding and ionic bonding. All right, so let's talk a little bit more now about covalent bonds. Now, remember that stability diagram that we did the other day, right? With the, that little fun exercise where the stability is gained as they get closer together, but then there's this repulsion of the two nuclei being too close together forces them apart, and we find this happy medium, this sort of sweet spot where the attractive force is counterbalanced by the repulsive force, and that's how we will define what the bond length is, or the bond distance. We have a similar stability of sharing the electrons. All right, they're not gained or lost, but by sharing, they still, each one thinks, if it had a brain, all right, each atom in the bond, in the covalent bond, thinks that it has a full valence shell. And in being a full valence shell, as you learned last chapter, that gives you the most stable configuration of electrons. Okay, so remember covalent, it's really like covalence, sharing of those valence electrons. Now, when we take a look at elements that do covalent bonding, right? Carbon will only do covalent bonding. And you may find in your travels amongst the compounds formed with carbon, that carbon will tend to form how many bonds? What do you think? 2, you said? 4 bonds, right? I think we all kind of appreciate that, right? Carbon tends to form 4 covalent bonds. You may recall when we discussed the periodic system, Mendeleev and the periodic system. And back in the 1800s, they had this other idea of what valence is. They still use the word valence, but it had to do with the combining power. Carbon tends to combine with 4 parts hydrogen for every 1 part of carbon. Remember we talked about that a little bit? It has a combining power of 4, meaning that when you mix it with hydrogen, you can find that it mixes with 4 parts hydrogen. So if we were to make a compound with carbon and hydrogen, it would look like this, CH4. Who knows what CH4 is called? Methane. Nitrogen, how many covalent bonds would nitrogen tend to form? What do you think? 3. Not always, it tends to. There are some examples where we'll have nitrogen involved in 4 covalent bonds. Oxygen tends to form how many? 2. And so on and so forth. So again, we can have a combining power of 3 with nitrogen, a combining power with hydrogen for oxygen, that's 2, right? When we mix nitrogen and hydrogen, there's your 3, NH3, that's ammonia. When we mix hydrogen and oxygen, the combining power for oxygen is 2, we have H2O. We all know what that's called. What's that called? No, what's it really called? Dihydrogen monoxide. Yeah, so be aware there's going to be some dihydrogen monoxide coming out of the sky today. So just, make sure you protect yourself. So when you start reading and watching and studying the nomenclature and how we name things, yes, that is dihydrogen monoxide, but of course, we also have common names for these. This is commonly known as water. So that's just the general trend, okay, for combining power. But we also see this as periodic trends. So if we go down a group, if you look at the periodic table that's here in the lecture hall, so group 4, carbon, if we go down a period, we'll have silicon. So what's the combining power of silicon? It's going to be 4. So we would have silicon, Si, H4, or germanium, H4. If we go down group 5, so for phosphorus, there's pH3. Arsenic, ASH3. You go down group 6, we've got H2S for sulfur, H2SE for selenium. Okay. All of these periodic trends, it's all based on the same periodicity thing. So if we can identify this pattern for the common ones that we're familiar with working with, as you go down a road, we can continue along the same trend there. So I'll just remind you in your notes, when we're talking about combining power, this was in the days of Mendeleev, just so you have that in your notes for that connection. We don't really talk about combining power anymore. Okay, so we're going to now study a new modeling system to explain covalent bonding. Remember in chapter 1, I talked a lot about models and symbols, and we use these to visualize what we really can't, but visualize in our mind what we really can't see with our eyes. And there is a model system from Gilbert Lewis, which does a really, really good job of modeling covalent bonding in compounds in a way that you can start with a compound and figure out what its overall connectivity is going to be, where the bonds are going to be, and then later on we're going to use that to come up with what the overall shape of these molecules are. And in doing that, we'll be able to make some very strong predictions about some of the chemical and physical properties of those compounds. That's actually the prize at the end of both chapters 4 and 5. First, we're going to start building these structures with models. And then from those models, we're going to interpret them to see, well, how will this behave in nature? Will it be polar? Will it be nonpolar? Maybe it will form a sort of a planar structure and be carcinogenic because it can fit in between the base pairs of your DNA and cause mutations, things like that. That's kind of why we focus on this. But for now, let's talk about this modeling system. Many of you may be familiar with it already from previous chemistry classes you've taken. We call it the Lewis symbols or Lewis structures, or sometimes they're called Lewis dot structures, because we're going to use a series of dots and dashes to organize the valence electrons around our molecules. All right, so this is sometimes called dot structures. And it's really a way to represent atoms and molecules. So the symbols is a way to model the valence electrons in atoms, and the structures is a way to model the valence electrons in compounds, in covalently bonded compounds. And it really is useful. You know, the best models are the ones that stick around. They have really, really strong predictive powers. Gilbert Lewis came up with this modeling theory back in 1916, okay? This was before quantum theory came about. Lewis had this way of modeling covalent compounds in a way that really gave us strong predictive powers. This is before all that stuff we studied in chapter 3. And I want to highlight that because as I take you through sort of these steps of building the model, it's going to look very similar to some of the things that we did study in quantum theory. But we don't know anything, or Gilbert didn't know anything about S sublevels and P sublevels and orbitals and 2 electrons in an orbital. They didn't know any of that. Okay, so here's how it's going to work. We're going to have an element symbol, and we know what those symbols are already. You've been studying those. So O for oxygen, H for hydrogen, and then the valence electrons are going to be a series of dots and dashes. And the dashes, in particular, these are going to be for shared electrons. All right, so if we just look at the symbols, the symbol, which is for the atom, if I were to draw the Lewis symbol for oxygen, it looks like this. We start with the symbol for the element, and that's going to be representing the atom. And then we're going to imagine that there's a box around this. Now, I'm only going to draw this one time as a box, just so you kind of imagine. We're going to fill in the 4 sides of this box, and we're going to fill them in with electron pairs. And we're going to do it in a way that looks like we're following Hund's rule from quantum theory, but we're not, because they didn't know about Hund's rule. It didn't exist in 1916, okay? But Gilbert's way of modeling how oxygen will behave, knowing that it's got a combining power of 2, so it's going to tend to form 2 covalent bonds. And in Lewis's system, well, here, let me show you how it works. So first of all, how many valence electrons do we have with oxygen? 6, right? You can read that off the periodic table. So we're going to put them in on 1 electron on each side. So we're going to, like Hund's rule, we're going to singly fill them. So 1, 2, 3, 4. And now we're going to stick the pairs in. And we only have 2 that are left for that. So 5, 6. Okay? So we're going to keep doing that, but we're not going to put the little box around it. So I'm going to erase my box. So now that you know what I'm doing. Now with Lewis's system, right, we've got either paired electrons, and you can see them right here. There's a pair of electrons, and we have unpaired electrons. And here's an unpaired electron. Paired electrons is very, very stable. And I've mentioned this to you before. Unpaired electrons are very unstable. So in chemical reactions, the tendency is going to be towards pairing up the unpaired electrons. That gives us more stability. So these are going to be the ones that are available to form covalent bonds. When you have unpaired electrons, they're very reactive. So we're going to think of these unpaired electrons as being available to form covalent bonds. And Lewis's system is really convenient for showing us that, because we already have this idea of the combining power for oxygen. What is it? It's 2, right? And here we have 2 unpaired electrons that are available to form those 2 covalent bonds. If we draw hydrogen, let's draw the Lewis symbol for hydrogen. What would that look like? It would be what? Just 1 dot. And it can go anywhere on any of those 4 sides. So I'm just going to put it over here. There's the Lewis symbol for hydrogen. Now, we know that when we mix oxygen and hydrogen, we make a molecule, dihydrogen monoxide, right? H2O. So let's show that now. And I'm going to keep my color scheme the same here. So here's my oxygen with the two paired electrons. So that's 4, not two paired. The two pairs of electrons. So that's 4. And then here are the two unpaired electrons. And then I'm going to draw the hydrogens like this. So you can see that in each case, the covalent bond is made by the sharing of those unpaired electrons. See, here we have a shared pair, and there's a shared pair. So this is now a shared pair of electrons. And this is, in fact, this is the covalent bond. But we also have, here, let's put this in red. We also have this pair of electrons that they started as a pair of electrons. They're not available for bonding as readily, right? This is what we're going to call a lone pair of electrons. This is also sometimes called a non-bonding pair. Whereas, since it's a covalent bond, this is also called a bonding pair. So that's the general idea. There's a lot of terms here to keep in mind. You got lone pair, you have shared pair, which are also sometimes called bonding pair and non-bonding pair. I'm going to use those interchangeably, so get used to those names. You've got the covalent bond formed from the shared pair. Now, I told you that we're going to use dots and dashes for these. Some of you who learned this in high school did all of your Lewis structures with the dots. And I'm going to ask you to not do that if that's what you're used to, and instead use a dash if it's a shared pair. Okay, we're going to still keep the lone pairs as dots. That's fine. But the shared pairs are now going to be the dashes. And the reason for that is when we start diagramming more and more complicated molecules, it gets really, really confusing if everything is in dots, whether they're shared or lone pair. This way, you can clearly see if it's a pair of dots, that's a lone pair of electrons. They're not involved in a bond. And if it's a dash, it's a shared pair. Okay? And those are the essential elements of the symbols that we use. And the rest of learning Lewis's system is learning the steps of how we use these diagrams to step by step build what is the most stable configuration of valence electrons in a compound. This is just to remind you of the periodic trends that I just focused on before. We had periodic trends in the combining power. We also have periodic trends in the way we draw these Lewis symbols. Well, here, Lewis symbols. It's just shown right up on here. I don't really need to say much on this one. Here's oxygen that we just looked at. And if we go down the group, here's sulfur. We have the same symbol for the arrangement of the electrons. And that's because these are all valence electrons. The Lewis system is only modeling the valence electrons. And that's all we need to model because those are the only electrons that are involved in bonds. So all of these symbols are going to look the same. So for carbon, carbon tends to form 4 covalent bonds. So all of these will tend, well, not 10, all of these by the Lewis symbol has 4 unpaired electrons. The unpaired electrons are the ones that are available for covalent bonding. And here in the middle, I didn't circle these. Here's your nitrogen, right? If we take a look at nitrogen here, let's just use that as an example instead of showing you the final product. If we were to do the Lewis symbol for nitrogen, we have 5 valence electrons. So let's fill them in. 1, 2, 3, 4. And then the 5th one, that's going to get paired up somewhere. So now we've got a lone pair. And we have 3 unpaired electrons available to make covalent bonds. So if I bring hydrogen in with this, just like I did with H2O, we would have one covalent bond there, one covalent bond here, and the third one here. Now we have 3 shared pairs. Okay. But again, if we're modeling ammonia in this case, I would ask for you to show it this way. But you got to show the lone pair. Yeah, question. That's a great question. So I was very careful to draw water this way with the lone pair on the top and the lone pair on the bottom. Could I draw it this way? Well, as long as they're pairs. Or could I draw it this way? Who thinks that any of those are okay? I heard somebody say no already. Who thinks this is wrong? Who thinks that it's right? Okay, why is it wrong? So both of these answers had to do with something we haven't talked about yet in lecture. That's going to be in chapter 5, okay? It has to do with the overall shape that this molecule is going to have in nature. And we're going to be able to interpret what that shape is based on the Lewis structure, okay? But this is a really important point that I want to start now, and I'm going to emphasize it. When we use a Lewis structure like this, as long as it is properly showing the right connectivity between the atoms and showing the valence electrons correctly with either lone pairs or shared pairs, it doesn't have to model what the shape will actually be. Okay? So in other words, if I were to do it this way or this way, those are both valid Lewis structures, even the top one. Now, when we get to chapter 5, you're going to recognize that the one on the bottom models what the actual shape will be in nature. And we will discuss later on why that is the case. But as far as the Lewis structure is concerned, the one on top is perfectly valid, which means that when we get there in chapter 5, you're going to need to learn how to interpret what the Lewis structure is telling you, even if it's not drawn exactly the way it is behaving in nature. Okay? Did I say that clearly with enough emphasis? I will be reminding you of that. All right, so let's continue along with another example here. Let's take a look at fluorine. Draw what you think the Lewis symbol is for fluorine. You've got an F for the atom, and then how many valence electrons? 7. So let's put them in. 1, 2, 3, 4, and then 5, 6, 7. So how many unpaired electrons do we have? 1. How many bonds do we expect to form with fluorine? Just 1. I should say, how many covalent bonds? Just 1. Okay. So when we have fluorine in nature, it's just floating around there. Remember that the unpaired electron is very, very reactive. So you're not going to find fluorine gas in nature looking like this because it's very, very unstable. All right. But if there's nothing around for fluorine to get that electron from, well, what else is there? All that's there is other fluorine atoms. And other fluorine atoms look exactly the same way. So let's put another one in here in red, but I'm going to draw it this way with its unpaired electron on this side, because these are going to come together. They're both unstable because they both have an unpaired electron. So they can both get stable if they form a covalent bond between themselves and share their, each of them shares their unpaired electron with the other one. Okay, so here we have our shared pair. This is our bonding pair. And that's our covalent bond. And then we have our lone pairs. These are the non-bonding pairs. And if we were to show this with our dashes instead of only the dots. So very, very clear. When we have fluorine in nature, by the Lewis structure, it looks like this. And when you draw these, make sure you don't go too fast and make sure that you are very clear about your lone pair electrons, your dots. Make your dots very clean and very distinct. So this is how it's found in nature. This is the most stable. And notice that in sharing, each one of them thinks that it has a full valence shell. Now, I didn't mention this on the earlier slide, but it's set up here, octet rule. It reminded you about the octet rule. So let me go back and just highlight that real quick. We talked about the octet rule back in chapter 3, when we were talking about when the S sublevel and the P sublevels are full, then you have 8 electrons, right? And we're going to take that same idea now with the Lewis structures. We want all of our atoms to be surrounded by or associated with 8 electrons. That's a complete octet. And that's what we have here, right? By sharing those 2 electrons, each fluorine thinks that it is surrounded now, associated with 8 valence electrons. Therefore, it's the most stable, right? And we're going to be using that as a check to make sure that as we follow every step in the Lewis structure model building, that we have complete octets for everybody. Okay, so this is the shared electron, okay? And in this case, it's shared equally between the 2 atoms. I'm going to talk about that in a little bit more detail in a minute, but right now I'm just going to say they're shared equally between the 2 atoms. And this is as it's most stable in nature. Now, when we see the compound written out as a molecular formula, it's also written as F2. This is how you find it in nature. And of course, we're going to be putting states of matter in with everything that we described. So fluorine gas in nature looks like this, and the molecular formula looks like this. This is called molecular fluorine. It's not atomic fluorine. It's how you find it in nature. There are a couple of other elements that when you find them in nature will also do this. It's called a diatomic molecule, by the way. And there's about 7 of them that will do this. And here they are: hydrogen gas, nitrogen gas, oxygen gas, fluorine, chlorine, bromine, and iodine gas. As a gas, all right? These will all be found in nature diatomically. Now, if you're interested in remembering that later on, because sometimes when you look at a chemical reaction and you try to decide, okay, well, here are my reactants and they're going to recombine and form products, you need to know that, well, gosh, if fluorine is one of my products, well, fluorine isn't going to be just one F by itself. That's going to be F2. If I'm doing a chemical reaction and I end up with chlorine as one of my products by itself, then it's got to be Cl2. So if you look at where these are in the periodic table, it's actually not that hard to remember what these are. Here's the periodic table. It's all of the halogens will do that. And then you've got nitrogen and oxygen, and of course, hydrogen's over here. So maybe that's not so easy to remember. Okay, there's only 7 of them. You could just memorize the 7. Or you can sing a little song. You want to sing a song? Yes, yes. So all of these have the suffix. They either end in GEN, like hydrogen, nitrogen, oxygen, or they end in INE. All of the halogens end in INE. So if your element ends in GEN or INE, it will combine in nature diatomically. So here's the song. Okay, ready? You're going to sing it too, all right? It goes like this: GEN and INE, are found in nature diatomically. Come on, now you sing it. Gen and INE. Hey, that's really good. You got it the first time. Usually I need to have the class do it at least twice to get it. So let's do it one more time. Gen and INE are found in nature diatomically. Ta-da. All right, now you'll never forget it, okay? Sing it every morning for the next week and through spring break, all right? And then you'll never forget these. For the rest of your life, you're never gonna forget those 7. Okay, so let's put a little musical note here to remind ourselves that we've got a little song, okay, to sing. Now, when we start building what the Lewis structure looks like on these, we've already seen one of them. Here's fluorine. Here's the Lewis symbol for fluorine. If I were to do it for hydrogen, you can probably figure that one out already without going through the rules of how you build a Lewis structure, because hydrogen only has 1 valence electron. So it's going to do the same thing. It's going to share that one with another molecule of hydrogen and thereby be most stable in nature if there's nothing else around for hydrogen to react with to become more stable. All of these reactions that we're describing happen because something's more stable in the products. So we're just describing how we find them in nature. Now, we can describe with Lewis structures what these other ones look like as well, but for you to understand those, we have to go through the actual steps of building a Lewis structure. So this is coming soon to a lecture near you, okay? We'll be building what diatomic oxygen looks like. It's gonna look like this, with a double covalent bond in the middle of it. But notice that by putting that double bond in here, each oxygen is still surrounded by, it's still associated with 8 valence electrons. 2 lone pairs, so that gives you 4, and then 2 shared pairs, that gives you the other 4. When we start building molecular nitrogen, you're going to find that it's got a triple bond in there. Each nitrogen has 1 lone pair and involved with 3 shared pairs, okay? So far, everything that's been involved in the bond that I've been showing you, except for water, have been the same atom on both sides of the bonds. Let's take a look at a case where the atoms are different. Let's make some hydrogen fluoride here. This is hydrogen fluoride gas. And here's the Lewis symbols separately, and then we bring them together, and we have the Lewis structure for hydrogen fluoride. Or if I want to show that with the bar, of course, we would do it like this. Now, here's our space filling diagram. So imagine that all the electrons are floating around in there somewhere. So here is the nucleus for hydrogen, and here's the nucleus for fluorine. Now, fluorine is a larger element than hydrogen is, so we expect the atomic radius to be greater. But if we imagine over this, what's the distribution of those shared electrons, right? This line implies that it's equal sharing, like I showed you before. All that bar really represents is that they're shared, okay? And with the exception of those 7 diatomic molecules, those are equally shared, as you're about to see. Everything else is going to not be shared equally. It's shared, but not equally. Now, models are very useful, don't get me wrong, okay? But models don't always explain everything. And that's part of the scientific method. When they don't explain everything and you find something new that it doesn't explain, then you need to modify the model. Other times, you just need to understand what are the limitations of the model. What does it tell you? What does it not tell you? In this case, the bar is not implying equal sharing. You need to know something else that's going on. And we're going to talk about that something else right now. It's called electronegativity. And to understand electronegativity, I'll just start by saying it's the same understanding of what we talked about at the end of chapter 3 about effective nuclear charge and radial distribution profiles and all that stuff. That will describe the periodic trends we discussed. It will also describe electronegativity. And I'll go into more detail about that in just a minute. But first, let me show you what happens. It's not shared equally. So how is it unequal? Well, we can describe that zone of probability around the hydrogen fluoride the same way. Those shared electrons are going to spend more time closer to the fluorine atom nucleus, than they are going to spend it closer to the hydrogen. And if you just even remember a little bit about effective nuclear charge in that discussion we had, as we went across the second period, right, as we got closer to fluorine, that effective nuclear charge became greater and greater. The attractive force that those valence electrons see coming from the nucleus. The same is going to be true for the shared electrons. They're going to see a stronger nuclear effective charge coming from the fluorine nucleus than they are from the hydrogen nucleus. So they're going to be more attracted to the fluorine. That's what electronegativity is really telling us. Let me give you your first definition for electronegativity. Right? It's the tendency to attract shared electrons in a covalent bond. If you remember, I talked briefly about electron affinity, right? The desire for an atom to attract electrons and how that went hand in hand with ionization energy. It's there in the lecture. You can go back and review it if you need to. It's the same idea. Electronegativity is very similar to electron affinity, the desire to gain electrons to form ions. But in this case, electronegativity, we're not forming ions. This is in a shared covalent bond. So these are shared, but they're not shared equally. So because of that, what's the charge of an electron? It's negative, right? So if it's not shared equally, and as I've described it here, those shared electrons are spending more of their time on the fluorine side of this bond than they are on the hydrogen side of this bond. What's that going to do to the charge distribution? Is it going to be equal? No, it's going to be skewed. One side's going to be more negative than the other. It's going to form what we call a dipole. A dipole, two poles. One is positive, one is negative. And when we talked about ion formation, gaining electrons and losing electrons, it becomes either a positively charged cation or a negatively charged anion. In this case, we're not gaining or losing electrons. We're just pushing them around so that they exist more on one side of the bond than the other. So we describe that with this little symbol here, this little squiggle, that's a delta. That's a lowercase Greek delta. Delta means partial. We're going to have a delta negative charge on the fluorine side of this bond because the electrons are attracted more to the fluorine than they are to the hydrogen. Fluorine is more electronegative than hydrogen. So when they are both sharing electrons, fluorine has a greater tendency to attract those electrons than hydrogen does. It's not a complete 1 minus, all right? It's a partial negative charge. That means on this side, we have a partial positive side. Dipole. We have a positive pole and a negative pole. Now, in more advanced chemistry classes, we actually can quantify what that dipole is. It's something that we call a dipole moment. And there's actual numbers that we could measure. Don't worry, we're not going to be doing that in this class, okay? But I do want you to be familiar with the overall symbol that we use for a dipole moment. And it looks like this. It's an arrow with the arrowhead pointing towards the delta negative side. And then we put a plus at the end of the tail. And that's on the delta positive side. And these dipole moments, they do have magnitude. And they also have direction. So for all of you mathematicians out there, this is what we call a vector quantity. That's for you. All right. But don't worry, we're not going to be doing that in this class. Although we are going to be thinking about the dipole moment in a relative term. You have to understand that they have magnitude, and you have to understand that they have direction. We're going to be using those when we get into chapter 5. Remember, 4 and 5 are going together, okay? Right now, you're just learning about what a dipole moment is. It's got polarity. When we get later on in chapter 5, when we start building molecules of things, okay, we're going to start looking at the magnitude and direction of that. So we're going to come back to this later. Coming back later, okay? Just a reminder to yourself, don't forget what a dipole moment is. So what this describes then is what we call officially as a polar covalent bond. The bond itself has polarity. Whereas if we go back up here, these are equally shared. So these are what we call non-polar covalent bonds. So this all really has to do with another term, the last term I'll introduce for today, and that's electronegativity. So to describe that, let me just use this slide, because this has some stuff on it that you're already seeing from chapter 3. Electronegativity, by definition, okay, this is just simply the tendency to attract the electrons in a shared covalent bond. That's more of a formal definition of what electronegativity actually is. But you can think of it the same way that we've already thought about ionization energy and electron affinity. And the trends are exactly the same. So I'm not going to go over again what ionization energy and electron affinity is. If you don't remember, go ahead and review that last lecture from chapter 3 and we talk about it, right? But the electron affinity, we can actually measure. We can measure that strength of attraction, right? That's when it's gaining electrons in forming ions. Here we're sharing electrons. So electronegativity, it's the same idea. We just don't measure it in the same way. But the trend is exactly the same. In fact, here we have a scale. This was from Linus Pauling. This is a scale for electronegativity. I'm just going to abbreviate that EN. So here, electronegativity EN. But just so you know, this is electron affinity here, and ionization energy was over here. So there's a Pauling scale for electronegativity, and this is a general scale. Okay, it's a relative scale. It's not absolute. And we can see it down here. Whereas fluorine, we've talked a lot about fluorine, has a really high a high electron affinity that we can measure. It also has the highest electronegativity. So when you have fluorine in a covalent bond with something else, it's going to have the strongest attraction for those shared electrons in the bond, followed by oxygen and nitrogen. These are going to be really the 3 most electronegative atoms that we have. Now you might see like chlorine has the same electronegativity as nitrogen does, but chlorine is also a lot bigger. So overall, if it's bigger, remember the nuclei can't get as close together. The larger the atomic radius is, it's a larger atom. So that's going to influence the distance between them. This is just a relative scale, okay? At the other end, all the way down here in the lower left-hand corner, you have francium. This is going to be the lowest electronegativity. So we're going to be using electronegativity a lot in our discussions. So probably what I'll do when we come back on Monday is I'm going to start by reinforcing this definition of electronegativity, because I kind of ran out of time here at the end. And then on Monday, we're going to start going through the rules of how we build these models using the Lewis symbols to model the most stable configuration of the electrons in compounds.